Good afternoon. So today we will make a now rigorous mathematical exercise by solving some model from beginning to the end, which will display this intermittency property that Simon introduced last time. So we will focus on a solvable intermittent model. So before writing what this model is, so we will first somehow derive this model from general considerations. So first we will be talking about motivation. What motivation gives a model, and motivation was exactly like we discussed last time, so that we expect that intermittency properties, among other also properties, they are not the properties of the unique just Navier-Stokes system, but these are properties of some large class. So this is phenomenon really for many systems. We want to understand which systems, right? And if you understand for which system that happens, you can consider the simpler systems, understand this phenomenon on simpler systems, and then carry over this knowledge to Navier-Stokes back. So so essentially we will construct somehow the minimal model. So like taking the minimum requirement that we need, and the requirement that we cannot discard is the scaling invariance. So the scaling invariance, the scaling symmetry is the only thing which was in the core of all the considerations. All the others properties we can throw away, but scaling symmetry we cannot, because scaling symmetry is essentially what was used in every argument related to intermittence. So, however, we can simplify a bit the scaling symmetry by going from continuous symmetry to discrete symmetry. So usually this helps. So what we do, we consider scales as now we'll consider scales as a geometric progression. So we take the first scale, which is the scale of our it's called integral scale. It's a large scale, the scale of our system, and we take it to be 1. The next scale we take 1/2. The next scale we take 1/4, and so on. So n scale will be 2 minus n, and so on. So we take geometric progression of scales. Usually, in these models, people are used to speak about wave numbers instead of scales. So wave number, and wave number is just inverse of the scale. So kn equal 1 over ln is to n. So the scales decrease geometrically, and wave numbers is inverse, so they increase geometrically from 1 to infinity. And then for each scale, we will consider the variable. So shell variable. Or no, let's get variable. Not even right shell. Variable. Like velocity. So at each scale we consider a variable, and in our models we just take it to be complex. But in principle, we think that this variable, it somehow mimics the fluctuation of the velocity at the corresponding scale. So just by in abstract form, so this is velocity fluctuation. Velocity fluctuation at scale Li. So what it means that we have kind of what we have in mind is that we have a turbulent motion which is full of different vortices of different size, and we kind of decompose it to the bigger ones, the smaller, twice smaller ones, and so the ones with size L0 and described by velocity U0, this L1 velocity U1, L2 U2, and so on. And the motion of each scale will be described by one variable. So the one observation is actually it's actually not an absolutely toy version of our dynamics, but exactly in this form you can see the solution of Navier-Stokes equations. So I just recall you that in harmonic analysis, this corresponds to what's called Littlewood-Pelly decomposition. And what Littlewood-Pelly decomposition, what it does, it takes the velocity field and it decomposes it scale by scale to the like simpler to the components where U0 only has variation of scale L0, U1 of scale L1, and so on. So there is this rigorous decomposition in harmonic analysis. So essentially, the difference from Navier-Stokes, in Navier-Stokes, each UN would belong to some Banach space. And here we substitute Banach space by complex numbers. So that's simplification. So simplification especially is taking the smaller space, so we can solve something. And then, as I said, the property we want to keep, is a scale invariance, scaling symmetry. Only. Later we can complexify the modeling, for example, adding the conservation of energy and so on, but and other symmetries if you like. But now we just we will try to on top of this setting we will try to compose a model which has a scaling symmetry, and that's it, and see what it gives. So if we are right in our hypothesis, it gives us intermittency. Right? And if it gives us intermittency, then we can think that the hypothesis is correct. So symmetry. So let's recall what symmetry means. So in the Navier-Stokes, remember the scaling symmetry was considered, as Montel, at small scales, where already you can forget about forcing, because forcing is just applied at large scales. And also, you can forget the dissipation, because viscosity you send to 0. So Navier-Stokes with viscosity going to 0, which is actually Euler equation, right? Euler equations. If you put viscosity equal to 0, you get Euler equations. And these equations we can write. So ut plus u grad u minus grad p to 0. So these are equations. And this equation has a scaling symmetry, which is sending time, space variable, and velocity to lambda 1 minus h time, lambda x, lambda h u. So this is symmetry, which we want to keep. And here it depends on two parameters, lambda real positive and h real. So for any parameters, you have this transformation, and this transformation just does not keep this all equations invalid. So if you just make it this change of variables, substitute in the equation, you see that this will be equation do not change. What that means specifically, so if you are given, let's write time first. So if you're given the field, so if you're given velocity depending on time and position which satisfies these equations, then you can construct a new solution. Which is obtained by multiplying u by lambda h. And then you have to put original time there. So this is t prime. So original time you have to divide by this lambda minus 1h. And then x prime you divide by lambda. So this is our old time. This is our old space. So this is a transformation. So this is all. If U solves Euler equations, this also solves Euler equations. This is definition of the symmetry. You can just verify. Okay, so now what we do, we restrict the symmetry to lambda equal power integer power of 2. So why we do this? Because we cannot just multiply by any number, since our space is now given by discrete scales. So if you want to go from one scale to another scale, you have to multiply or divide by 2 or any power of 2. So this lambda in our system cannot be any positive, but it can be any power of 2. So essentially what it means is that we can relate any two scales. So just let's take a two subsequent scales and divide by 2. So this is a case, for example, lambda equal 2. Lambda equal 2, it changes the scale n, move it to scale n plus 1. So then what we do, remember that instead of this object, we have now just un. So now our variable is not a field, but just collection of variables as function of time. And it sends this solution to, so we keep lambda h, we keep time, as it was. Oh, let me write it in the same way as it was. So we map it to new solutions of t prime, which are lambda h, u, minus h. And now if we divide by lambda, and lambda is 2, this is essentially changing ln scale to ln plus 1. So all you put is n plus 1. And this is true for lambda equal 2 and h arbitrary. So let's not write it here. So that means that the symmetry is now like reads in the form TUN mapped to lambda 1 minus h t lambda h un plus 1. So this is discrete analog of this symmetry. So from this symmetry, we go to its discrete version, and here lambda is 2, h real. So we have the symmetry. Certainly, this is just for lambda 2, but this symmetry can generate already symmetry for any power of lambda. Just you apply it twice, it will be symmetry for lambda 4, and so on. And if you make an inverse transformation, then for lambda 1/2, 1/4, and so on. So this will generate the symmetries for all lambda which are powers of 2 instead of just real numbers. So this is a symmetry we want to keep. So this is discrete version of scaling symmetry. So next step is we want to construct equations. And how will you construct equations? So our space can be now labeled by number n, which labels our scale. So at each n, we have a variable, un, which describes scale here. Then we'll have n plus 1, and is described by next variable, n plus 2, n plus 2. And so on. And we want to write now equation of motion between these variables. So what means equation of motion? Essentially, in the physical language, means that they should couple. So the change of these variables should depend on itself. So it couples to itself, and also it may depend on the neighbors. So it should couple to neighbors, and so on. So this is a coupling. Also, in principle, what we remember that we have at certain scale, the scales do not start from infinity. There is a certain cutoff, so there is a kind of forcing part of the scales where we'll force the system so it keeps alive. And in principle, there is also scales which correspond to dissipation in real turbulence where the energy is dissipated. But remember that I said that we only keep scaling symmetry, so dissipation we will not need to put because we don't need energy so far. So not now. But we will, on the next lecture, we will already have it. So how you construct? Constructing scale invariant equation. We can give a kind of simple recipe how you can construct that equation and making sure that it will be scale invariant. Essentially, you go back to Euler's system. And what you can notice is that scale invariance is actually imposed by these two terms. So what you do, you replace the first term by derivative of your velocity at scale n in time. And then you think what these terms mean. So these terms means, so each u you can replace by something like un or the neighbors. And the gradient, if you remember the gradient, its Fourier transform of the gradient is ik, right? I by wave number, and we have these wave numbers. So wave number is inverse of the scale. So we have this kn here. So we just put kn. So it means that what we put in order to keep the symmetry, we can use terms like kn un squared. So essentially what is important is that there should be kn prefactor, and it should be quadratic in un. That's or un or n plus 1 minus 1 doesn't matter. But so that's all we need to ensure the symmetry. And now you can construct as many models as you like by just putting different terms here, which have this shape. You have many models. So what we do, there are different strategies. The strategy that what was very popular in physical literature is just restrict the coupling to nearest neighbors. So you can restrict the coupling, just the derivative of n only depends on two nearest neighbors, of 5 nearest neighbors. And this limits, or this gives you all the type of terms that you can put here. And it turns out that you impose extra condition on conservation laws. This is essentially uniquely defined. So this is one strategy that we will look at in the next lecture. So now what we will do is a different thing. So I will just give a model which is constructed with the only purpose that it can be solved by hand. Yeah? And the model itself, maybe equations are not so compact, but essentially model was done by the inverse engineering. So you first understand hidden symmetry and then construct a model that you can solve. So, but we will go in opposite directions. So first I give a model, and then kind of it will be a miracle that we solve it. So solvable model. So what we will use un, and we will use n not just complex, but we remove 0. So our model, it will not be 0. And then, so this n will start from 0 as before. And then on the when we talk about coupling, so this is un. So the coupling that un minus 1, un plus 1. The coupling that I will use only coupling with itself, with an A, and with the previous neighbors corresponding to large scale. So why it helps is because it will help, since it's not coupled to the smaller scales, you can always cut the system, and it gives you finite number of ordinary differential equations, so you don't have problems with existence uniqueness. So you don't need to care about what happens here. So this is just a trick. So okay, so then this cannot go forever. So we remember n starts from 0, and that. So what I will already put the boundary of forcing condition u0 will be just 1. So it's like you can think that you have a cup of tea, and you just, on larger scale, you keep turning the spoon. So this is 1. And equations, so the equations of motion. du and dt. So first, I say, remember, so all our terms should be of the form kn un squared. So first term, I put exactly kn modulus un squared. And then we, in principle, can multiply it by some factor. I will just tell you in a while what this factor. So this factor should have such a form that it doesn't break the symmetry. And this is exactly interaction with itself, right? So un to un. But now I want to put interactions to the previous members, and I do it just in the same form. So we sum it up. So un, and then there is a sum of all scales which are on that size, m smaller than n, and then it's a real part of, and then I write it to kn, and then I couple it to um. So um. So this is a physicist notation. Star is complex conjugation. Okay. And then I also would put this prefactor. So that's it. That's our model. This will be defined if I define f. Right? So what is f? So f n. It will also depend on u, but in a scale invariant way. So what the form, specific form, is like this. Okay. So it depends only on un and un minus 1. And it has one more function inside. So this function is f and z is a C2 function that maps C without zeros squared to because it has to has to.
But f is from 1, n divided by.
Well, f is a function. Okay. Oh, yeah, you're right. No squared. Sorry, you're right. It's not written squared, but I thought that it might. Good. And to okay, to itself. But important is we're not dealing here with holomorphic functions, just C2. So it's essentially we just use a convenient notation, complex notations, but actually it's not about holomorphic functions. So it's not holomorphic differential.
So the complex part on the right-hand side can come only from the first term.
Un is by itself complex. Yeah. So complexity. It's more to say that we put. You see, since we have modulus, so it's essentially two different equations for real imaginary parts. So there is no big importance about complex structure in that case. Okay, that's all. So, so exercise that you can just do and just verify scale invariance. So you can verify that if you forget about boundary condition, because boundary condition always break invariance, it just cuts the scales. So if this equation would be on all n, the change of variables in this form with any h and lambda equal 2 will not change the form of this equation.
Inside the real part, shouldn't there be index m also in the case of k?
No, that k is n. K is, I hope. Let me check. M, yes, it's M. Good.
We're also not forcing and not anticipating as well. We're not forcing.
Not forcing. No, we're forcing. We are putting U0 is 1.
We're not adding terms.
No, we don't put plus F, but we're forcing it by putting something on, which is never 0, which doesn't become 0. Good. Okay, so now we are going to show that this can be solved. And how you do this, you write rescaled equations. Rescaled form of equations. So rescaling will have two pieces. First, we change both state variable and time variable. So we take a double transformation. So the first we we define multiplier, which is defined like Wn will be Un divided by Un minus 1. And also we define rescale time. Rescale time we define like the tau n will be dt divided by Tn. So we kind of we should introduce time scale, and time scale. How you introduce the time scale? So remember that time is length divided by velocity. So which length we take? We take the length of the scale where we are, and we will not use the same velocity because then it will just kill the modulus. But we will use the previous the velocity. So we will consider the smaller scales driven by the larger scales. So we divide by the scale by the velocity at previous scale. So this is it, and this is what? So L is 1 over Kn. So this is 1 over Kn Un minus 1. So in other words, d tau n is Kn Un minus 1 dt. So that's first transformation, second transformation. So you see, we change time dynamically, right? So it depends on variables and so on. So it gives you for n we get different time. So now essentially that's what I'm kind of trying to I'm introducing variable at each n and time at each n. So it will be many times. We'll see that that's essentially the whole the essence of this of the intermittency. So now okay, let's write equation of motion with a new variable. So tau n is this business. So it's 1 over Kn Un minus 1 ddt of Un minus 1. Okay, this is okay, so we differentiate separately. Kn Un minus 1 squared n dt. And then it will be minus, so this part, so it will be Un Kn modulus n minus 1 cube. Okay, remember that modulus is what? Modulus is square root of Un minus 1. So both terms are reconstruct from the equations of motion. So now we substitute equation of motion. Well, let's use this property. So one more step. Okay. So with simple exercise, you can check this. When differential check this is true. And now you substitute equations. So you substitute our system. And what you will see is that you see every term of this part, well, I think I will not make derivations, but you can check. Just substituting, so the right-hand side is tuned in such a way that everything cancels. And what you get at the end is f of Wn. Good, no? So that was the whole goal. So
Surely it was constructed by Segal.
surely it was, of course. Yeah, yeah. No, if you will never you hardly succeeded in that form. Yeah. You should go. It was done in backward direction, and you understanding that the idea of time scaling. Okay. So anyway, what we get is that using this variable and this time, you get a system which is very simple. For each n. Yeah? For all n.
But I'm sorry, may I ask one structural question? Was dun by dt contains some inside? Yes, and I don't see what sum can cancel.
Well, you get one sum here, and then you get un. You see, un minus 1 star will multiply this un minus 1, which gives you modulus, and it cancels with the denominator. So what will be rest is this real part sum, and it will cancel real part sum in another term. And then you will see that this term also, in this term.
There you have dun minus 1 by dt. Yes, okay. Okay, now I can be. Yes.
Yeah, there are two terms.
Two sums
Two sums cancel each other. Yeah. One sum comes here, and this part cancels the. Okay, and this another sum comes here.
The miracle happens for all n or just from
For all n. Every n, including the first one. No, for n from 1 forward. For 1, 2, 3, 4. There is no. N is defined starting. You see, since this is n minus 1, so n can be the smallest n, taking into account this condition. The smallest n is 1, and it's also true.
the sum in the inside goes from
In that case, sum, yeah, it comes, in that case, sum, when you put forcing, you always break the symmetry, right? But the sum, so putting this forcing, your m is bigger than 0, of course. So m is from 0. So this is scale invariant equation, and you have to put forcing condition. Forcing condition fixes u0 and cuts this sum.
Is it important that it's complex? Can it be dimension 1 real?
Yes, true. It can be dimensional 1, but I think in dimension 1 we will not get intermittency. We will see that we will need periodic solution, and in a dimension 1 it's problematic to have periodic solution.
So this property holds for every f.
For every n,
What about f?
f is the same. F is, any given function. So there is only thing which is missing is at time, because each system evolves with its own time, and then let's see what does it mean. So let's differentiate the next time with respect to the previous time. Let's see how the times are related. So you put this formula, so it will be kn plus 1 modulus un dt by kn un minus 1 dt. So kn plus, it gives just 2, right? And this is modulus of wn. Okay. And the last thing that I want to put is tau 1, d tau 1, d tau 1. So it will be k1 dt. This is 1. Actually, we have to put it to 1/2. Then it will be just 1. But OK, so this is 2. This is 1. So this is 2 dt. So tau 1 is 2t. So we have a system where first we have time which is original time up to constant 2. But if you it can be done that, well, if you divide by 2. Well, the t1 is originally not our original time. And then you have a first box is dw1, d tau 1 equal f w1. So essentially, the box which is given gives the dynamics of w1. Right? So given by this system with respect to this time. The next, given w1, when you solve this system, you can find the next time, right, by solving this equation. Because to find the next time, you need to integrate previous solution. So given solution of this system, you find tau 2. Given tau 2, you integrate next variable. Given next variable, you integrate next time. And so on. So that's a system, and this is so this is what we have. I can kind of anticipate what hidden symmetry means. Because we will not directly introduce it here, we'll introduce it tomorrow, because here we don't need hidden symmetry since everything is solvable. Already for the systems more complex, we will need to understand, but here you already see what it means. So now, in terms of these variables, you can take all the times together with all variables and map them, just shift them. The shift is certainly the symmetry, and this is what will be called hidden. What will become a hidden symmetry? So why it is a different symmetry? Because remember that we constructed model based on recovery or based on scale invariance, and scale invariance is a family of symmetries labeled by H. So there is H involved. Here there is no H. So unlikely it is correspond to, there was no any H, specific H to select. So that means that this symmetry is not equivalent to symmetries that we had. So this gives a different symmetry. Actually, it gives a different symmetry which is generated by those symmetries. You will see that it's kind of a fusion of these images. But this, so we get this. We will not use it now. But what we will do is we now try to. We will now continue. Now we will specify f, solve the system, and now we have. So what you do, you can solve them sequentially, but at the end we have to go back to original variables. Okay? So what are the original variables? Original variables is that un. Remember, so this un is wn by the modulus. Then you can do the same here. And so on. So at the end you get the formula that un is wn modulus wn minus 1 w1. So that's formula for un. So if you want to get un, you have to solve all this system until wn and take a product. And then we also need to know what is time. dt in the same way you can is d tau n. So dt, you can put it in below, and then you use this formula for un minus 1. So it will be kn also product. So this is how you go back. So we have we will make it solvable by choosing good f, and then we can go back. Make a break, maybe. Okay, so let's. So now, to make it completely solvable, we need to say what is f. And idea is simple because equation is on a plane, so a complex plane. So this real part of w, imaginary part of w. And so what we will do for f is we will consider the equation with a limit cycle, with stable limit. So we will take some loop, and we consider the loop, which is so what the loop will be. So the loop is z equal r theta e theta, not w. So this will be our limit cycle, so the attractor. And we take f such that whatever point you start, so that this is a stable limit cycle. So it's it should approach it from both from inside and from outside. So this is stable limit cycle. So we know how to do it rather well from differential equations. So we take f of z W, no? To be R theta, be R d theta minus rho. So this will be, so we say in polar coordinates rho, W rho e theta minus rho plus E rho. This is our function, so the differential equation driven by this function has this limit cycle, and it's stable. And not only this, you can write explicit solution. So let me write explicit solution. I will explicit solution. I will not derive it. You can just check that it is, because that's more or less standard. So the solution is W. So solution of system, which is dW d tau equal W is W tau is R sorry. So you so where what is phi is given by the initial condition. So E is the angle of phase of W at 0, and R is absolute value minus R. So these two constants are given by the phi and R given by the initial conditions, and then you see that as time is large, this term goes to 0, and you are left on just on that vector. And so you have a distance R, and you just follow that vector. So exponentially approaching that vector. We assume for further purposes, so that obviously the R should never touch 0, because we want to avoid 0, and also for some other reasons, which will be needed later, we also assume that R plus the R d theta is also positive. Just some so in order to these two conditions, so this condition avoids passing through 0, and this also avoids some singularity further on. So okay, so for any R, we have a function f, and we have explicit solution. So now we have to with having this solution, we want to reconstruct the original the dynamics in original variables. So first thing we can state, there will be two theorems that you can prove. The first theorem we essentially already proved. So for any initial condition, which is not 0, there exists unique global in time solution for our model, and further on every component is bounded. So it means that there are two constants. So small cn, which is positive, which bounds n, and there is big cn, which is also which is finite at all times. So these two, of course, depend on the initial condition. At all times. Well, how to see this? You have to do a little work. So essentially, in order to see that you have a global solution, we obviously have the solution for each global solution for each W. So the only thing that you have to complete the proof is that when tau n goes to infinity, correspond to t goes to infinity. So there is no finite time singularity. And this you show. This is technical. I will not show. And then this is also, this is two constants. They essentially coming from representation of un as a product. And then you can just show that every component is bounded, yeah, because the loop does not touch 0. And you can just prove that you can always bound the function. So this is a.
But capital N can go to infinity if n goes to infinity.
There is no capital N.
Or capital C.
Yeah, capital C. No, they depend on initial condition, and I'm not claiming anything. As n goes to infinity, yeah, of course.
And moreover,
I'm just talking about telling that every single component is bound.
moreover, if error of theta, maximum error of theta is bigger than 1, minimum, then typically
Yeah, the one can go to,
will
yeah.
go to infinity,
Yeah.
small c will go to infinity.
And this is one of the fingerprints of intermittency in some sense. So they're bounded, but oscillations become wilder as you go to large n. Okay, so now we go to intermittence. So do we have intermittency in this model, and what it is? So intermittency, kind of qualitatively, intermittency means that, and we will see that it's true, that if you, so it's complex, so let's put model, absolute value. So it means that at small scales, the behavior is intermittent. What means intermittent? That something happens, but from time to time. Yeah, so there's sometimes it becomes large, then small, then it's middle small. So this is intermittency, and this qualitative picture becomes more profound the smaller the scale. So that's qualitative part. What intermittency means. So it all like visually, if you put graph, measure normalized to the peaks, you will see that for small scales it's almost always just doesn't move. From time to time it just goes up. Yeah. So this is intermittent. What it means analytically is measured by scaling laws. Laws which Simon introduced. And remember, the scaling laws were about the moments of velocity variation at scale L. And here we have direct analog of this, because velocity variation at scale L is our un, right? When L equal Ln, so this becomes un. So then it means that we can put a structure function of any order p. Usually we write as function of Ln, but in fact it's just function of n, of course. And then it's equal to the modulus of un t, taken in the power p and averaged. And average is with respect to time. So remember the average with respect to time is what is a limit. When time goes to infinity, 1 over t integral of this thing dt. So this is the structure functions. So first let's write what it means for intermittency, then we'll try to associate it with the picture. So what we will show is the power law scaling. Is that each structure function is proportional. This is a question. This means equal up to constant to ln in the power zeta p. So far, this is the first part, and the second part is what. What it means is that if you put structure function as p, you put ln. It starts from L0, right? L1, L2. So it should be power law. Or how we rather used to plot a logarithmic scale. We used to plot minus log 2sp. No, let's put log 2sp. We will put here, it will be n, which is minus log 2ln. And here it will be minus log 2 sp. And then what it is, if you take log, it's just straight line. So this is minus zeta pn. Because this is what? This is 2 and zeta p. So if you put log 2, you get minus n zeta p, right? Minus, no? Do you agree with this? So this is just picture. What means power law? Okay, in different coordinates. So now for usual signal. So if the signal is not like this, a usual, and remember that if it's scale invariant, what you usually expect, so what you may expect is that zeta p will be equal to some prefactor h by n. So this you can do. So if the solution was scale invariant, p, okay, then the values of zeta p as a function of p would be straight line. So this is scale invariant solution. Scale invariant solution for fixed p. Fixed h. So remember we had the symmetry. So if the solution is also scale invariant, so then you will have this. Well, let's not waste time to see exactly why. What is important is that in our case, it will be something like a curve. It will be nonlinear. So this is intermittent. This is self-similar. So why is it so? You see, this shape means that whenever you take large p, this moment will decay slower, no? Because it curve goes, so they decay slower. And the way it decays slower for the power of p is to put pikes. Because when you take an average, the contribution of pike will be just its width, which is always the same. But the maximum will be taken in power p. So this is how the intermittent picture magnifies higher order moments. So this picture means that when you take p large, the thin peaks will give a stronger contribution for the larger piece. Because the peak is large, so the piece order is making it even larger, and it comes with the same weight, which is a time, because it's average in time, so it's the time length. So essentially, you only, whenever you have this behavior for the moments, it essentially implies that behavior is intermittent. Yeah.
But it's usually higher than the exact solution of p over 3 in the lower moments. This model gives a contribution that is higher than the p over 3.
Well, I'm just talking about large p, and we're not discussing the p over 3 because p over 3 has to do with conservation of energy. We don't have conservation of energy. Just I'm only trying to distinguish straight line from a curved line. So the curved line, straight line means that if the line is straight, you can just give a sign for un, and for higher un, you just multiply sign by certain constant, and all moments will scale like this. But with the sign, you can, whatever you do with the sign, scaling and so on, you cannot get this picture, the curved picture. For the curved picture, this larger n, more piked it should be. So this is the only way how you can have zeta p smaller than the something which you expect from a straight behavior. So this is intermittency. So now we will see this. I'll show the picture because this is exactly what happens. But now let's compute exactly let's compute these moments. So the whole interest in this model is that we can compute structure functions. I will keep this picture. So let's try to start here. So I will. Yeah, I can first state result, and let's first state the result. The second theorem is the following. So we have this function r. So let's r0, actually the mean value of r in angle. So the mean over the angle, so which is 1 over 2 pi. Here, theta by theta. Let it be transcendental. Remember what it is? Okay, then for any p real, SP ln is exactly ln zeta p with zeta p equal minus 2. So just from the moments of this function, we get the 2. And certainly, if you take this function with log, we will have example, but generally you automatically have non-linear dependence, which means that intermittent behavior for the model. So for essentially, except for the circle. So if you take a circle, yeah, so then this will, if it's circle, then it will be a radius in the power p log 2, and you see it's proportional to p. So if it's circle, zeta p will be proportional to p. So it will be self-similar. If it's not circle, it will be intermittent. So how to prove? So we need to compute time averages. And we know that, okay, time average, and then remember that your n modulo of n is just product. From n to 1, let's write it in opposite direction. And each of them goes to its attractor. So we can already discard the transient behavior and then see that it's already an attractor. So this is the, it gives us, so modulus of un. We can just consider solution on attractor. So remember that, so w n tau n, it goes to r theta n, with theta n is a sum function. Oh well, theta n is actually tau n plus constant. So this is our attractor. So we're on a circle. And the direction. And the phase just goes linearly with 2. This is our solution. Okay, so that means that we can substitute it inside. It will be modulus r theta n. Modulus r theta n. Good. So everything, all the problem is now in thetas, because theta is theta can be just replaced by tau, because it's equal to tau up to a constant. But problem about times is that now everything, all the troubles about times, they are linked to each other. So every time. So every time behaves differently, and but we have to average with respect to original time. But every term lives in its own time. So how to do this? And now what you do, if you compute, so you make a computation. So what we do is that d theta n dt equal d tau n dt. Remember, so there is no difference. The only difference between angle and tau is just up to constant because of the initial condition. And this we have it. We just wrote it there. So it is this is kn product from 1 to n. This one. So we have, for each n, we have a kind of complicated equation which we need to solve. And the way how, but we can solve it. So we can prove a lemma is that there exists a change of variables. So, and I'm doing this change of variables in special way. So I take it exactly theta n and all other previous with some function which I don't care. So the why this is good is because you see the Jacobian of this change of variables will be 1. I'm not changing the volume of the phase space. Such that in new variables, the equation becomes just Kn R0 and minus 1, which is R0 is just average. So somehow I'm substitute each term by the average of R. So I'm making a clever change of variables so that right-hand side become a constant. This was not constant, now it become constant. This is technical part, not very complicated, but I will skip the proof. So this is what? This is quasi-periodic motion. This is motion on the torus. Because alpha n is still on a circle. Its modulus 2p. So alpha n in a circle. So this is a periodic motion. It's motion on a circle. But each mode it has different frequency. So the last thing is to use transcendentality of R0. So Sergey already knows. So if R is transcendental, then all these quantities, which will be K1, K2 R0, K3 R0 squared, and so on. So all these frequencies are rationally independent. So it means that you cannot take finite number of them with integer coefficients such that sum is 0. So there is no resonances between them. And then there is a theorem which is called Kronecker from dynamical system, Weil theorem, which tells then the dynamics of alpha 1, which tell that the dynamics of alpha of these alphas is uniquely ergodic. I'll tell you what it is. With uniform measure. With a uniform invariant. So just we need to translate what the last sentence means. So the last sentence means that uniform invariant measure means that whatever, if you take time average of whatever function of alphas in time, is the same as just taking average in alphas. And uniquely ergodic means that this happens for essentially all functional and all initial conditions, right? So let's just this directly, and then what we can also do. So the same is true. The same is true for thetas, because the Jacobian was 1. So the change of variables didn't change phase space, and also for people from the dynamical system, what is important is that the system always it's not a system which is fully coupled. You always truncate at each n, and then the first n equations give an independent system. So this is so you can use all the theorems for the finite dimensional dynamical system. So I never use the infinite dimensionality here. So let's just apply this to computation of structure functions. So this is SP of UL is time average of UNP in time. Ergodicity means is that we can average it with respect to thetas. So no, first let's open it up. So we can substitute UN by its value on the attractor. With respect to time. And each angle function of time. But now by ergodicity we can ergodicity means that you can replace time average with respect to angle average. So what it means exactly is that you take 1 over 2 pi power n, integral from 0 to pi of this sum, of this product. We average with respect to angles. But this is a product, so it decouples. So this is just one average. Any power, we forgot P, no? So it should be P here, P here, P here, P, and here it's N. Now remember that what it is. This is exactly, so what it is, this is exactly, okay, so let's write it in the following way. So it's average of RP in theta n. Now this average we can express from this zeta p, so it's 2 power minus zeta p. This is 2 power minus zeta p. So this is 2 power minus n zeta p. This is ln. That's it. So we computed that every structure function scales exactly as a power law, and zeta p is this model. So what we do now, I will show you example how it works kind of numerically, so see what you get, and then we discuss. Then we will discuss. We will analyze how all this picture relates to the constructions that Simon was doing during the last lectures. Remember this mu infinity measure and all these properties of the measure.
Question, yes. So here you used the fact that you converge to a circle, yes, and basically you can explicitly. But of course, some ergodicity properties should be enough.
Exactly. Yeah. We do.
It's correct.
Essentially, the whole it was done in order to get. You see, you need to have some ergodicity property, but usually ergodicity property is not an easy thing to get. Especially, it was uniquely ergodic. So
Yes, because for unique ergodic you lose
Completely. So it's tough. No? Is rare. So that's essentially the point. So certainly we know very well that. So in that case, our system is quasi-periodic with infinite frequencies in the limit, and we know that turbulence is not like this. And the kind of the curious element is that this infinite dimensional quasi-periodicity was one of the first was basis of the Landau theory for turbulence that he was put in one of the first editions of the fluid dynamics of his course. And then after the development of dynamical systems, it became clear that you cannot have a structurally stable, robust quasi-periodicity for the dimension more than 3, starting with 3, which means that turbulence cannot be infinitely dimensional quasi-periodic, and this part of this chapter was removed from a book. But this is exactly kind of the version of the turbulence system which would be quasi-periodic within infinite dimension. So that's I like it for this reason.
When this model was introduced?
No, this?
This model.
This is my paper of 2021. I will show you some pictures, and then we will. Will it work? Hopefully. So now you can play in the games as Simon likes. So you can take different function of R. So we take function R. So it should not be circle. So if I take some addition, so it will be, I think it's ellipse. Then you get something non-trivial. So you take this function. This is a mean. So you see that mean is transcendental. And then you can compute zeta p's just from the formula that we have, where it is. We can compute all zeta p's. Here, zeta p's were computed by the referee. so thank you. If you see, so that zeta p's is this function. Yeah. For every p. Well, I stopped at this formula. Well, you can certainly compute for every p, but for any p, you have to think a little bit. And then, so what it gives dependence of zeta p on p in this shape. Then you can compute this structure function as function of n, just to verify it works. So numerically, so this is points which compute numerically, and the red line which given by theorem. So since it's and they completely match, so as it should be. And now I'll just show what means intermittency. So what it implies. So this is the first picture are all UN. So there's a modulus. So the blue is U1, red is U2, yellow U3, and so on. And you see that the smaller the scale, they oscillate faster, but also the pikes become thinner. And you can see it more precisely by looking at them each by one. So this is U10. So you can already have a very clear footprint of intermittency. So it's kind of nothing happens, poof, peak. Then nothing happens, strong peak. The stronger the peak, it's thin it is. So then some peaks appear, then nothing happens for a long time, then there is a peak. So this is intermittency for U10, and it should become worse smaller the scale. So this is U20. So it's essentially zero compared to the peak. So it's zero everywhere, and then there are very fine peaks from time to time. So this is intermittency. And this is what we see in turbulence. Was it?
P is equal to 1?
So,
P. Yeah, P is equal to 1.
which?
Usually we compute.
No, this is dynamics. This is not structure functions. This is dynamics. This is how U10 depends on original time. So this is you have a system of equations. They're all coupled. That bigger original model, and I just integrate it with respect to time. And this is solution for the 10th variable. This is solution for the 20th variable. So bigger the n, so the smaller the scale. Scale, I mean what we call the scale, and the more intermittent it is. So this is intermittency. So this is exactly the picture that you have to have in mind, and the power loss with nonlinear dependence of exponents on p is a mathematical formulation of what it is. What is intermittency in turbulence? It's not the same intermittency that dynamical system like to call it, but this is numerics of the model. This is numerics of the model. Okay.
Interesting how you keep numerics for calculate. Because I mean, it's a hard story.
Well, a computer, you just put in. Okay, so now we want to summarize and a little. Think of what we have and what is the connection essentially with what we learned from the phenomenological theory of turbulence, measurements, and so on. Conclusions. So first, I know you have to press. No? Ah, okay. And then you have to press here. Okay, good. Sensor. So first, what this model gives us is an invariant probability measure. Which Simon was writing as theta star. So how it gives us a measure? So let's remember what is UN. So UN is eta theta. So the probability measure is supported on the attractors for each variable, right? So for UN at long times, UN will be sitting on a set which is given by phase and by the product of functions R. Remember, this is our formulation. So and for every n, where theta 1, theta 2, and so on are uniformly distributed. So you can think that the measure which corresponds to this distribution is the same as telling that these are IID random variables with uniform distribution in a circle. So the measure, so now you can just define the function. So let's define the function, which let's call them, it's M. Let's define the function which maps these angles to velocities by this formula. And mu star is just mapping of the uniform measure here to this space. So mu star, it will be just push forward of the uniform measure on angles. So we have explicitly the mu star measure in this case. So this is good. Also, the good part is that we see that this is a measure which is supported on infinite dimensional manifold, right? Because essentially it's a product of the loop of each direction. So it's infinitely dimensional at measure. So the limiting measure is complicated, yeah, but we have it explicitly. Then also we have ergodic theorem here. This means that whatever function that of you have, and you average with respect to time, it's the same as averaging phi with respect to this measure. This is what Simon used multiple times. So time average equal measure average. So here we do have it. We have it. Also, there is a rather direct connection with the model that we considered on the last lecture. So what you can say is that modulus of un is a product of. So let's take modulus of un. So it kills the phase. And I put it in opposite direction. Where theta i's are IID, which means that we can just call this R1, R2, Rn. And the statistics of the measure tell that all of them are. So it's such that you can interpret all of them as IID random variables. With a proper distribution which is given by this map. And remember that in the case, on the last lecture, what Simon showed is that he did it like this. He represented un as a product of 2 minus h1, 2 minus h2, 2 minus hn with IID h1 hn. Like was like this, right? So this is essentially the same. Well, exponents are ID, and he is just up to notation. It's the same thing. So we directly recover this probabilistic description, but now we recover this probabilistic description with we don't assume a probabilistic description. We recover them from deterministic equations of motion. So we have a link directly from equation all the way to the end. So to the definition of the measure and to the computation of structure functions, exponents, so on. So everything on this model, everything is real. And the last thing is symmetries. It's also important to understand what role it plays here. So remember, so what the scaling symmetry was that T un was mapped to T1 minus 2, no? Lambda 1 minus, okay, let's put lambda 1 minus T, lambda HU, and where lambda is 2, H is real. So this transformation also transform a measure. Well, change of time doesn't matter for the measure because it's invariant, but this will change just measure for each component by lambda h. So what you can see is that
It goes to n plus 1, right?
good. Yeah, and shift the measure. So what you see is that if you consider our measure far from the ends, so on so it essentially it scales and shifts. Certainly, the measure is not scale invariant for any h. So whatever h you do, you can apply this transformation of the measure, just like push forward, see what, and compare it with the same measure, for example, on certain scales in the middle. It will be different. And it's of course different because if it would not be if it will be true, then we would otherwise zeta p equal ph. This you can, if the measure is scale invariant, then you derive linear dependence. So we don't have linear dependence. We know that measure is not scale invariant. So all symmetries are broken. All scaling symmetries are broken. For the stationary state. At the same time, we have a symmetry which is, we do have a symmetry. Remember that we had the symmetry which we called hidden symmetry. Hidden symmetry, the symmetry with respect to new times and new variables. And this symmetry is restored because it maps attractor to attractor. So essentially it maps measure on this, invariant measure on these variables to measure invariant measure on these variables. So it is restored. For mu star, I'm not explaining, writing it exactly how it's done formally. This we will do in future lectures, but that's essentially the whole motivation for the further studies is that it turned out that on this example we see that we have intermittent model which automatically breaks all scaling symmetries, but there is some symmetries changed after rescaling time and rescaling variables which get restored. So what we are going to show is that this symmetry can always be introduced, provided that you have this. So this symmetry actually follows from that. It always exists. And this symmetry generally can be restored even if this symmetry are broken. So this symmetry is weaker. And whenever this symmetry is restored, we automatically have the intermittency. So we automatically have the power loss for structure functions, and we can even make sense of what are zeta p. So essentially what we will do is we will on the next lecture we will make exact sense to this for the already similar model, but already where we cannot solve it. So where everything is keeps coupled. Of the next lecture, we will show that this can be extended directly to Navier-Stokes Euler equations with some extra complexity. And in the next lecture, we will show that actually equations do not matter, only symmetries matter. So essentially, this symmetry is a consequence of commutation relation of the symmetry group. So that's a plan. Huh? Oh.
Like the picture that you showed, the intermittency, you can interpret it as like these are like clocks ticking, right? And then when they start synchronizing, you have peaks.
Yeah, very good, very good thing. So how you can thank you. So how you can think about intermittency coming from this picture? So every variable so on a complex plane we have a attractor. Yeah? So something which is not a circle. And at large time, actually our variable sits on the attractor. So it's Wn is a function of tau n is exactly as R tau n just turns around. So how you get intermittency? So every variable, for every variable, they are not synchronized. This is exactly the condition of transcendentality. So they are not synchronized. So for every n, the motion kind of in large time, it's kind of independent from the other. So the peak you have if when, at the same time, un is a product. So when you have a peak, if at those instances where many of them go through maximum. And this is and bigger this product, rare is this event. You see, so when you have n larger, so scale smaller, in order to get the maximum, all of them should synchronize at this point. And this happens more rarely. So that's why the peaks become more rare, and their duration is smaller because the larger n faster is the motion. So the big peaks become more rare, faster, and that's it. And most of the time, these phases are not synchronized, so you have something which is a product of the smaller values. So with large n, it becomes infinitely smaller than the peak. So you have almost zero and then peak. And this happens at large time. It resembles random behavior. No? This is exactly the Kronecker-Weill theorem. So it becomes random. So next, we continue here.